In this video, we look at parabolas, and specifically we are going to look at the parameters, the effect of the parameters in the three different equations that represent parabolas. We will look at the characteristics of a parabola, and we will go through some pointers on drawing the graph of a parabola. So let's start off with the standard form. Now, the parameters that I refer to are the variables like a, b, and c that are generally represented with a number. Okay, so the x and y remain. Those are our two variables that we normally have in the equation. Okay, so each parameter affects the graph in a certain way. Okay, so for example, a tells us about the shape of a parabola. Okay, and if a is positive, we know that the graph is what we've called smiley face. Okay, now the correct term for that is concave up. The cave opens up, if you like. If a is a negative value, we have a sad face parabola, or concave down. The cave opens down, if you like. C represents the y-coordinate of our y-intercept on the graph. Okay, and B is very useful to find two things. Okay, one is the x-coordinate of the turning point, and the second is the equation of the axis of symmetry. So B is not equal to these, but B helps us to find these. Okay, and it helps us because it is part of this formula. X equals negative b over 2a. So a is also helpful in this regard. Okay, so if we use this formula, we will find the x-coordinate of our turning point, and that x-coordinate is also equal to the equation of the axis of symmetry. Next, we look at the turning point form of a parabola. Y equals a times x plus p all squared plus q. Again, a tells us about the shape of the graph. Okay, if a is positive, we have a concave up graph. If a is negative, our graph is concave down. Okay, q is the vertical shift. So if q is positive, the graph is shifted up by q units. So shift up q units. If q is negative, the graph is shifted down q units. Okay, now P, is important in two regards. P helps us to find the x-coordinate of the turning point. So both P and Q are involved in finding the coordinates of the turning point. Okay, so coords of turning point. Okay, now the y-coordinate of the turning point is the exact q value. Okay, so q is our y-coordinate, but the x-coordinate we find by taking what is in the brackets, so x plus p in this case, making it equal to 0, and then solving for x. So in this case, I would subtract p and I'd get x equals negative p. So my x-coordinate of the turning point would be negative p. Okay, then p is involved in the horizontal shift. Okay, now p is a value that is added or subtracted to x. So the way the horizontal shift works is that if I am adding a positive value to x, so adding a positive value to x, the graph shifts to the left. Okay, so adding a positive value to x, shifts the graph. That's right, shifts the graph to the left. Okay, now the reason I paused earlier is this is counterintuitive. Okay, adding a positive value, so x values, we know that the positive x values are on the right and the negative x values are on the left. If I add a positive value, I move in the opposite direction towards the negative x value, so that's to the left. Okay, so adding a positive value to x shifts the graph to the left by however many units you are adding, so by that value. Okay, so for example, if we had x plus 2 in the bracket, okay, I'm adding positive 2, okay, what happens is that this shifts the graph 2 units to the left. Okay, so 2 units left. In contrast, if I add, so adding a negative value to x, shifts the graph to the right. By that value. Okay, so for example, if I have x and I'm subtracting 3, so adding a negative 3, that means my graph has shifted 3 units right. Okay. And the final form in which a parabola can be represented is the factorized form, also known as the root form. Okay, because the R1 and the R2 represent the roots of a parabola. So the roots, and another name for the roots, are the x-intercepts. Okay, so this equation becomes very helpful to us if we have to find the equation of a parabola where we are given the x-intercepts. And again, A represents our shape. And again, where A is positive, our graph is concave up, and where A is negative, our graph is concave down. Now, it is very important that you know the details of these 3 equation forms very well, and that you understand the effect that each parameter has on a parabola. And to visually see the effect, there is another video that I will be posting on that, where I show it in GeoGebra. So make sure that you watch that video too. But going on to the characteristics of a parabola. So a parabola can be concave up or concave down. And as already mentioned, concave up, you could consider as where the cave opens up. So if this parabola is the cave, the cave opening is upwards. So this graph, this first graph on the left, is concave up. And for the whole domain, so the domain of a parabola, unless restricted, is x is an element of R. So this graph is concave up for x is an element of reals. Okay, the graph on the right, if we consider, is concave down, where the cave opens downwards. Okay, and again it is concave down for the entire domain, so for x is an element of real numbers. Then each parabola also has a maximum or a minimum value. Now this refers to a y value, okay, and that is important to understand. And it occurs at the turning point. Okay, so a maximum value is a maximum y value of the graph, okay, beyond which the graph does not exist. A minimum value is a minimum y value of the graph, beyond which the graph does not exist. Okay, so the graph on the left has, if we look at the turning point and its y coordinate, the graph exists above that y coordinate of the turning point, not below. So this y value is a minimum turning point. Sorry, minimum value. So this graph has a minimum value of y equals, and it is -4. If a graph is concave down, we have a maximum y value. So in this case, the maximum value is the highest y value beyond which it doesn't exist, and the graph is below. Okay, so this graph here has a maximum value, and that maximum value is the y value of +4 in this case. Right, increasing and decreasing. Now, one parabola both increases and decreases, okay? But obviously it's different parts that increase and decrease. Okay, so if we look at the first parabola on the left, okay, an increasing graph means as I move from left to right, the y values decrease, okay? And a decreasing graph means as I move from left to right, the y values decrease. So, the graph on the left, as I move from left to right, the first thing that's happening is that the y values are decreasing. And that changes at the turning point. So, this graph decreases for x is less than, the x coordinate here is 3. So, for the x values less than 3, the graph is decreasing. Okay? So, x is less than 3. But then after the turning point, the graph increases again. So as I move from left to right, the y values are increasing. So it increases for x is greater than 3. The graph on the left, on the right, starts by increasing. Okay, so as we move from left to right, the y values are increasing. That changes again at the turning point. So it initially increases and then it decreases. So we say that it increases it changes at the turning point whose x coordinate is -1. So where x is less than -1, it increases, and it decreases for x greater than -1. So both graphs increase and decrease, but at different points on the graph. Now each parabola also has a stationary point. Now this is a point where the graph neither increases nor decreases. So a point where the graph neither increases nor decreases. This occurs at the turning point. Okay, so I have a stationary point there and a stationary point there, and we can refer to them relative to the x values. Okay, so this graph has a stationary point at x equals 3, and the second graph has a stationary point at x equals -1. Domain and range. Domain is all your x values for which the graph is defined, which means, for example, if I were to select an x value, say 6, if I could draw a vertical line, and find the graph, it means that the graph exists for that x value. So if I choose another one, x equals 5, okay, that's an x-intercept, so the graph exists on x equals 5, on the x-axis there, okay. If I choose x equals 4, okay, if I draw a vertical line and find the graph, it means the graph exists. Even 4.5, vertical line, I can find the graph, it means the graph exists, okay. So the domain is the set of all x values where the graph exists. Okay, now we know that parabolas continue unless they are restricted. Okay, we know that they continue forevermore. So unless restricted, every parabola's domain is x is an element of reals. Let me just move this there. Okay. So let's look at the range. Okay, now range is different. So the range is all the y values for which the graph is defined. Now the y values start on the y-axis, and I find the graph if I draw horizontal lines. Okay, so if I pick a y-coordinate, say y equals 1, and if I'm able to find the graph with a horizontal line, it means the graph exists. Okay, so that's x equals 1. If I choose x equals 3, horizontal line, the graph exists. Okay, so the range is all the y values for which the graph exists. Okay, now if I have a concave up graph, then the range will be y is greater than the y coordinate of the turning point, which is my minimum value. So in this case, specifically for this graph, let's just change the color. My range is y is greater or equal to the y coordinate of the turning point, which is -4. Okay, so then in general, if my graph is concave down, which happens when my a value is negative, then y will be less than or equal to the y coordinate of my turning point, which is represented by q. Okay, so specifically for this graph, okay, my range is y is less than or equal to the y coordinate of my turning point, which is +4. Right. Then every parabola also has an axis of symmetry, which is a line that runs vertically through the turning point of the parabola. Okay, and if we are asked to sketch it, so we only sketch it if we are asked to, we draw it with a dashed line. Okay, now it's an axis, so it's a line, and of symmetry, which means that the graph is symmetrical on either side of that line. So graph is symmetrical or mirror image on either side of that line. Right. Finally, I just want to make some comments about drawing the graph of a parabola. You have this year already drawn many graphs of parabolas, so I would just like to make a few points. While you are allowed to use a calculator to find a table of values to help you sketch the graph, it is also important that you are able to find the x or y intercepts, the turning point, and the axis of symmetry if you are asked to. So refer to page 94 in your workbooks to look at that example, okay? But what you can really do is use the table form on your calculator, find a table of values, and sketch the graph. Now when you sketch the graph, so just some drawing tips. And these I take from your investigation that we did in the first term. Draw a neat line. Okay, so no, a neat line is a solid line like that, not sketchy. Okay, I don't want to see any sketching like this. Okay, it has to be accurate. And make sure the coordinates of all your significant points are clear. So your significant points are your turning point and your intercepts. Then finally, extend the arms of your parabola to the end of your grid. So if you are drawing a parabola, don't be like, oh, okay, there we go, and just stop there. Okay, first of all, this is not a neat line. I'm not passing through one of my points, and by not extending my arms, I'm missing my y-intercept. Okay, so be very accurate. Make sure that your turning point is clear, x-intercepts are clear, and your y-intercept is actually part of the graph. Okay, so extend the arms.